So I'd like to start by reminding you where we were, and in a big sense and a smaller sense, and then we'll go from there. So just a reminder that our central player, or two of our central players, are the following. There's the Grothendieck ring, where we're fixing a field, a base field K, and we're defining the Grothendieck ring R, which is going to depend on K, where we take, it's a ring, the additive generators are just classes of varieties up to isomorphism. The additive relations are generated by, if you cut something into an open and a closed, then you want to make that into a sum in the ring. And then lastly, multiplication is just multiplication. The products are products, or at least for varieties, and then you can extend to everywhere, extend to everything. And then we have something which is this name, the motivic zeta function, which is, you take a variety, and what you spit out is you take sim n of the variety, and that the generating function for the sim n's. So this is it's a power series whose coefficients are in the Grothendieck ring, and because this behaves well under the cutting and pasting, it means that in fact gives you a map not just from varieties, but even from the Grothendieck ring itself, R, with its additive group structure, to, well, this is always going to be, sim 0 is 1, so it's 1 plus stuff, which is invertible, and addition goes to multiplication. So that's that's where we were so far. And maybe I should just first ask if there are questions about things that have happened that will help things go forward more easily too, about any of this. Okay, so why is it called a zeta function? So last time we considered this in the the version in the topological CW complex category, and we saw Macdonald's theorem, which said that Macdonald's theorem, which told us that the generating that the analogous thing, we got something which is a rational function. And so where we left off was to try to understand what this zeta function is doing, is to look at a finite field. And great. And so here we don't know exactly we don't know what the Grothendieck ring is, but we do have this point counting map. We take a variety over FQ, we count the FQ points, the rational points, over the base field, and that is a motivic measure. That is a homomorphic image of the Grothendieck ring. When we take the zeta function, the motivic zeta function, we can apply this point counting map, and we get something which is in Z double bracket T, and this is, it turns out, the Weil zeta function, the topic of the Weil conjectures. And I should say, I mean, the Weil zeta function is usually defined as follows, or I learned of it, and I feel like maybe this shows that I prefer to think geometrically than arithmetically. I feel cheated by the definition you usually hear. And the definition I heard was you take a variety over FQ, and you count the points over every single field extension, you put them in a generating function in a slightly weird way, you exponentiate, or well, I forget, you massage it a little bit, and then you get this thing which is rational. So you have to, but I think it's as a geometer, I think it's much cleaner to instead just say, take your variety and all its symmetric powers and just count the points. Generating function, no massaging, that's it. So, and so it's an exercise, depending on a fast or slow exercise, depending on your experience, that this is actually, that the image really is the Weil zeta function. And okay, so we like the Weil zeta function a lot. So this is a clue. This is some richer version of the Weil zeta function. And Weil's reason for introducing a zeta function was because of his thoughts around the Weil conjectures, or more generally around this Rosetta, what he called the Rosetta Stone between arithmetic geometry, or maybe number theory, algebraic geometry, and topology. And so I want to notice that our two examples of zeta functions in the sort of very arithmetic setting and also back in the topological setting, we got rational functions because we know that this is a rational function. So this leads to a natural question, which I think really should have been asked. I'm surprised it was not asked by soon after Weil. Well, I guess we needed to have the category, but people knew about varieties. People knew about varieties a long time ago, even before Grothendieck. So the question, which was asked, to my knowledge, the first time I've seen this question asked was in 2000 in a paper by Caprana. But it's not even a paper. It's an unpublished preprint, which is on the archive, as I mentioned. And the question is this, which is this rational? Is the motivic zeta function rational? So I'm going to try to convince you that the answer is yes, and that we should want it to be yes. It is yes. It's got to be yes. And so let me try to convince you of this. But first, I should give you some evidence. And so some evidence would be, well, okay. So so the first bit of evidence is that it's true for curves. And if the curve has a rational point, this gives a proof for, this is an easy proof for the Weil conjectures for curves. If it doesn't have a rational point, there's some subtlety that Daniel Litt worked out, but it's also rational in this case too. So that's evidence. It's also true over C. Maybe I should say, now, okay, this we care about K being a finite field, but this statement works anywhere. I mean, I can ask this, as long as I'm asking, Tony, I'll ask for 10 times more money than Tony did. So I might as well ask for it. So over the complex numbers, then we could specialize to Hodge structures, and it's true. And this is the thesis of Chia 94, again, remarkably late in history, given what goes into it and the motivations and the proofs. And I'll talk more about her thesis later, later today. But that's more evidence. It's rational then too. And then also, if over FQ, if you do point counting, it's true as well, because we know the Weil conjectures are true. We know that, so somehow in these different lands, it seems always to be true, and that's a lot of evidence. But I want to say that even better in some sense. So we have evidence that agrees with things we know. We can prove cases, and even better, if it were true, it would of course imply the rationality of the Weil zeta function, and it would imply it in what I think is a really good geometric way. It's not by looking point by point. It's saying that you can see this by actually cutting and pasting the symmetric powers and seeing that they follow some sort of recursive pattern. So that would be a very geometric proof of at least the first part of the Weil conjectures. And in fact, it should that work, then it should actually give proofs of most of the rest. The Riemann hypothesis wouldn't be probably attackable directly in that way. But I want to say also this has strong consequences even over the complex numbers, where we already know about Hodge structures, and that's the following thing. So let me just point out something about something obvious that you've undoubtedly seen before. That if I've got a function, if I've got a power series, let's say, and it's the quotient of two polynomials, then what this means is if you multiply it out, then this power series times a polynomial is a polynomial. This gives a recursive recipe for computing all the coefficients of f once you know the first bunch of coefficients. So if I tell you I've got these polynomials, g and h, I'm not going to tell you what they are, but I'll tell you their degrees, and you can figure out the first two values of f, then you can figure everything out. So there's a finite amount of information in some sense. And so if we had rationality of the zeta function, then over the complex numbers, it would mean that there's some recipe to actually take varieties, give me a variety, tell me its topology, its cohomology groups, and tell me the first two symmetric powers. And I can build all later symmetric powers by cutting and pasting and taking products and things like that. So that would be nothing like that. Nothing like that was known or dreamed to be true. So there we go. So we have a statement, this rationality statement. It's short, it's beautiful. It generalizes things we know. It implies things we love to know. There's lots of evidence. So this is the right approach to the Weil conjectures and to all things related to it. Okay, so this is a wonderful thing. And indeed, theorem, this is due to Mike Larson and Valerie Lentz, in the early 2000s well, sadly, it's not rational. So I find this a really, a really amazing result. I guess a yes would be an even more amazing result. But that's because we have, we don't know what this ring is, and we understand it only through having various Euler characteristic kind of things, and every single thing we could think of was indicating that it should be rational. So they had to think of a new kind of Euler characteristic that would somehow demonstrate that a function is not rational. And I should say, if I give you a generating series, how do you prove the coefficients? If I don't tell you much about it, how do you prove it's not rational of any degree? That's a non-trivial question. But let me now turn this negative into a positive, which is that we now have this Grothendieck ring where we don't have rationality. And I'm going to work over, say, FQ. And we have the integers, so we have the V zeta function, and we have the motivic zeta function, and somewhere in between here and here, it becomes rational. So far, our proof of rationality already is way down here. But here's an example. My vague question is, where does it become rational, and should that tell us how to prove it? And maybe here's an example. We've already talked about localizing at L. At that point, it might be rational even here, because their proof involves some Euler characteristic where L is 0. And when you localize at 0, everything blows up or goes into a black hole. So their counterexample does not apply. So very possibly this is rational, and that's good enough for all of these other things. So for example, to prove the Weil conjectures, that's good enough. You're counting points. It suffices to let Q count not just in the integers, but in the integers with Q inverted. Yep?
So is there a counterexample over a finite field?
Oh, that's a good point. There is no counterexample over a finite field. So no, yes, there's no known counterexample over a finite field.
So what field are they working on?
Complex numbers. So they need the complex numbers for this to be workable. And so I should say, here's another question, which is a new idea is needed, and I could imagine these are the sorts of ideas that you just don't, that somehow come to you, as you're falling asleep or waking up or on a bus. Could it be true over finite fields? If it's, I should believe it should not be true, but any way to show it's not true, any provable counterexample would be really cool because it requires some sort of a new insight.
Before we put this one on top of the other one,
Mm-hmm.
what exactly is the statement over C that you have said? It's true for curves over C?
It's true for curves over C. It's false for some surfaces. The counterexamples are even surfaces. So things go wrong even in dimension 2. Okay, so at this point we're kind of disappointed and frustrated because we'd hoped to get a one-line proof of rationality of the V zeta function, and it didn't exactly work out that way. But just to get your hopes back up, let me retreat to the complex numbers again and look at our third example of how we get a hold of our third example of motivic measures, which was Hodge structures. So let me recall Macdonald's theorem, which I mentioned last time, which is designed in the topological setting. And then we're going to go algebraic because we know that once things are algebraic, there's more structure that we can try to build on. So the zeta function was equal to, well, I said in terms of Euler characteristics, let me put it this way. It's 1 minus t to the h naught, 1 minus t to the h1, 1 minus t to the h2, and so forth. So I said it last time as no sum. Great. Last time I just said it's 1 over 1 minus t, the Euler characteristic, but I'm deliberately going to separate the Euler characteristic into different kind of cohomology groups. And when the cohomology has additional structure, then you could, again, hope that this makes sense to, that we should be able to enrich this. And indeed, so let me tell you the theorem of Chia, which is the following. Actually, let me put this on the next page. I should keep these in a pile so at least they come reverse ordered in the end. So here's the theorem, and let me state the theorem, and then I'll say what the terms mean. So here, X is a complex variety, may be singular, maybe singular, does not have to be compact. Then the generating function, I want to keep track not just of the cohomology groups, which is with compact types of sim n, but we have additional things. We can also take what's called a Hodge structure. And the Hodge structure involves taking this complex vector space, takes C coefficients, and there's some way of expressing it as a direct sum or filtration of things that are indexed by two additional things. And maybe that's all you really need to know. And then you can pick off the dimension of these pieces. And now let's get a generating function for that. And we had t to the n already, but let's also mark x to the p, y to the q, and minus z to the r, just for, well, I won't say anything about that, but the minus sign. And then there it is. That's a generating function in more variables. And she says that's rational too. That's the product over all p, q, and r of 1 over 1 minus x to the p, y to the q, z to the r, t, and the power to the power of minus 1 to the r, h, p, q, or maybe, no, that's right, I think, of h, r, x. So in other words, to put this, what you should notice is that all you need to know to work out everything are these invariants just for x. And with that, you just take this thing, 1 over 1 minus something, take the product over all possibilities, and bingo, you get it. And this specializes to, in the case, this specializes to this because you just set x, let's see, you just set p equals q, set x equals y equals 1, and z equals 1. And yes, great, and that's it. So this is a much richer version of this. So now this is, I want to generalize, because when you see something like this, you should hope for something better. These are dimensions of vector spaces. And so there's this sort of this call to action these days where people stand firmly and say categorify. And by categorify, that all they mean is you see a number, it should be a vector space. That's well, they mean sometimes a little bit more than that. But in this case, what I want to do is do something which keeps track not just of these numbers, but even of the vector spaces, because in some way, and then applying dimension in some sense will result in this. Okay, so now I'm going to try to make this work. So I'm going to try to state and prove, well, prove modulus of maximum is a theorem. But I think the way mathematics often is done is you state the theorem first, and then you try to figure out what it means so you can actually prove it. So I'm going to state it first, then try to make meaning out of it, and then actually prove it. So I won't get there right away. Let me just say what are Hodge structures? If you really squint, they're cohomology groups, they're vector spaces with some additional information. What about when you're counting points, as was discussed in Tony's talk just now? If you want to count FQ points, if you know about étale cohomology, you have étale cohomology with the action of Frobenius, and that will tell you the number of points. So it's a vector space with additional structure that you want to get mileage out of. So here's what I want to do. So I want to have something that I'm going to call, it's going to be cohomology-like. So what does that actually mean? Well, it's going to start off. We'll start off with varieties, and we're going to map. I guess this functor, I'll call it hi for each I non-negative integer, and I want to get a vector space, but I want some additional structure. And we'll worry about all this later on. Maybe Hodge structures, maybe a group action. Maybe this is a clue Hodge structure should be seen as in terms of a group action, and I should say that it's a vector space, but I'm not going to even, there's no reason for it to be a vector space over the same field. In étale cohomology, you don't want to do that often, or you don't want to do that. And so we'll do this over a field, and you'll see soon that it'll help for it to be characteristic 0. So even if k is not characteristic 0, but you'll see that it's forced on us anyway. Okay, great. And this additional structure is going to, so vector spaces we like because we can direct sum, we can tensor, we can take sims and wedges, and I want everything to play well with this more. So, and that's true for Hodge structures, group actions, and everything like that. So I'm allowed to use words like this and this and this, and things like that. or det or anything like that. Okay, so cohomology is supposed to be functorial, so this should be a contravariant functor. And I'm still kind of agnostic about what I mean about this. And so we want to talk about Euler characteristics. And what's an Euler characteristic? It's to be an alternating sum of the cohomology groups. So we're going to want to be in the Grothendieck group of these vector spaces, which means that just all I mean is formal sums plus you're allowed minuses. It's like virtual representations, formal sums of vector spaces. Great, so that's where the Euler characteristic is going to lie, and it's going to be the sum of so we now have this Euler characteristic which lives here, and I want it to be the alternating sums of the cohomology groups, except I'm going to get confused if this is an infinite sum. So I guess we'll also require that hi is equal to 0 of x for I sufficiently large. And then this makes sense, and we're happy. Okay, so we don't even have long exact sequences or anything. That's all. I'm asking for really very little. Okay, so there's our axiom that we're going to require, so we can even make sense of Euler characteristics. So far, I've not done anything really bad or illegal. What I've done is I've just sort of abstracted what works in the Hodge theory case, where it's vector spaces with more structure, and we know what Euler characteristics are, and that's basically it. Okay, so now here's the theorem, which makes no sense yet, which is that, what do we want to say? We want to say that the zeta function in this world, I guess the zeta function doesn't really have a name, but it is take the symmetric powers and take their Euler characteristics and just add them together. There's no square brackets because we're already living inside this thing, whatever it is. And so I want to say that, okay, if you tell me about x, I will know exactly what, I will tell you everything about all the symmetric powers. And so here's what I'll do. So for example, in the case of Macdonald's theorem, this would be Euler characteristic with compact support. In the case of Chia's theorem, okay, now I'm confused because that's a vector space. And so how do you take 1 minus t to the power of a vector space? And so I should say this should be interpreted as a power series over our Grothendieck, over this thing here. So it should look like this. It should be it should live inside here. Both sides live inside here. Okay, great. So, but what does this mean? How do you take powers? How do you take t to the power of a vector space? Well, okay. So t to the so what is 1 minus t to a vector space? Well, it should be, well, what's the binomial theorem tell us? It's 1 minus v choose 1 plus v choose 2. There's no way to, it's got to be this, plus minus v choose 3, and then plus, and then the last one will be plus or minus determinant v times t to the dimension of v. Great, and now that's a polynomial now we're living in the right place. We have a polynomial whose coefficients are these vector spaces with additional structure. So there's no, great, so that's not alarming, and this is now a conjecture, a statement. Yeah, it's a statement as a falsifiable statement. I've got, there are my definitions. There's my, that's what the things mean. Maybe one thing I should point out is that 1 minus t to the v times 1 minus t to the w is 1 minus t to the v plus w. So addition turns into multiplication, which should sound familiar from things we've talked about before. Maybe if you want a fun fact to try out yourself, you could 1 over 1 minus t to the v. Well, not, so I told you what that is, and that's in terms of wedges of the vector space. That's the generating function for the symmetric powers of the vector space. And you should say, wait, that looks, there we go. I see that zeta function-y thing looking right there. So, so this should be extremely suggestive. In the category of vector spaces, that is the zeta function. Everything is looking really good. You're getting this sort of universal description. And now we want to somehow do this in this far more general setting. Okay, so now we have a theorem which makes sense. And now I want to prove it. But to prove the theorem, okay, I don't know how to prove this theorem. But if we add a few more axioms, we can prove it. And it's amazing how little you need to know. So I'll tell you 2 more axioms. And I should say that you should think of these axioms as what you need to make this proof work, and then you should say, aha, someone should have thought of these axioms, but someone did. His name was Grothendieck, and so one nice thing about this is we're following in his footsteps, not by reading what he said to say, oh, of course this is the right definition because Grothendieck said so. Instead, we're saying, okay, well, here's why Grothendieck had this idea, and yes, this absolutely makes sense. It's better. I always find that as a better way to learn things. So here's another axiom. I'm going to want the Kunis form. This is the Kunis formula. I want to say that this is true, that you have I won't say it should be functorial and blah, 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 but basically the cohomology group should satisfy. This should be, the cohomology of a product comes from the cohomology of the pieces, and that X is a Y. And then maybe, so that's now the third axiom. The final axiom I want to say is the following. So if T is a variety, and you have a group acting, a finite group. So this is an honest variety and a finite group. How hard could that be? Then you've got this map to the quotient of T by the finite group. And that means, because cohomology is a functor, we can take cohomology classes of the quotient and pull them back to cohomology classes of the source. So we have that map. And now here comes the axiom. I want to identify this. This identifies H I T mod G with, well, okay, so I should say G is acting on T. So again, because cohomology is a functor, G is acting on this vector space. So we have a G action on the vector space. And I want this to be identified with the invariance. So which is an extremely reasonable thing to be true in all reasonable cases you can think of. It actually is true for ordinary, usual kinds of cohomology. This was proved by Grothendieck in his Tohoku paper. I forget where the little hat goes, so I'll just abbreviate it that way. Okay, good. So we want these axioms. And now, given these axioms, I will prove the theorem. I will essentially prove the theorem. And leave one bit to you that I think I would try to convince you that that's absolutely doable. Okay, and it's going to be a short proof. Okay, so we know, how do we get the symmetric, how do we get the cohomology of a symmetric power? Well, so it's going to be, that's x to the n mod the symmetric group. So by the third axiom, we know this is going to be the same as, or by, yes, the third axiom, it's the Sn invariance of the cohomology group of the nth power of x, where Sn acts by permuting the factors. But we also know but we also, by the Kunis formula, can turn this into some complicated thing, involving just the cohomology groups of x. And you build it up. Well, it's not hard to figure out how to build it up, but you have n things. Well, I'll let you think about that, but you can write this easily in terms of that. So now we've turned already the cohomology of this into things involving just the cohomology of x. That's all we need to know. And I should say that the invariant, that's why we need characteristic 0, not for any fancy reason, but just because we want to be able to take invariance and representation theory of finite groups works better in characteristic 0. And awkwardly, we can't even pick a characteristic because n is going to get arbitrarily large. Okay, great. So now I basically want to say we're done, modulo a check, which is that now we have this, I want to say there's a universal description. For any x, there's some description of the cohomology of n of x in terms of the cohomology of x. And there's a recipe that works for every single x all at once. It's purely, now there's no geometry left at all. And so we want to prove, well, let me just go back to the statement and see where, and gesticulate at it. So this is what we want to prove. And we now have described this power series in terms of all the cohomology groups of x. Every coefficient, we have a recipe, and that we have. And then this one we have too, because that's how we know how to make sense of this. And now it's a purely formal algebra combinatorial question to actually just, all you have to do now is check that this is true formally, that you write this in terms of h naught of x, h1 of x, h2 of x, and so forth. Write down the generating function here, write down the generating function here. And if you're algebra combinatorially minded, you'll recognize what you're doing, and you prove it's true. And then you just have this universal theorem, which you can then go hit with, which you can then go, you have this huge hammer, which you can then go around hitting people with. Okay, so let me mention some corollaries. So if you applied this to Hodge structures, well, we've just proved Chia's theorem. So that just comes out right away. If we applied this to f counting to the Vey zeta function, so we use the counting map, and so in this case, so Tony told us that we could find that we could interpret this as in terms of the étale cohomology. He took, I think, QL coefficients is what he used, and you have Frobenius, I forget what letter he used maybe something besides F for it, acting on it. And the number, it's not hard to prove, and Tony stated, so I can then, if Tony said it, it must be true, that the number of points is the alternating sums of the traces. So you have this sort of trace map. Okay, so here we go. Now, what we have is our vector spaces with additional structure are QL vector spaces. We happen to know, the facts about étale cohomology is that, let's see my axioms. First axiom, HI is 0 when I of X is 0 when I gets sufficiently large. Second axiom, the Kuhneth formula holds. Third axiom, that Grothendieck-Hooke argument applies basically just fine for that as well. So it all works. And that means that we can now prove that, now I'm going to look at this theorem and use this for QL vector spaces with F, with the action of F. And I've got this. I just apply trace. And we proved the rationality of the Vey zeta function. That, boom, we're just, it's just done. So that's pretty, this is why we like rationality, but in some sense, this is why we like the standard conjectures too, because these three axioms, the three axioms, which I won't flash in front of you again, are very, there's so little in to get such amazing output. And again, the fact about Hodge structures was not known, probably suspected until the mid-1990s. And there's no reason why soon after Hodge this shouldn't have been done. Okay, so now we see good reasons for zeta functions to be natural, to be rational. Really, the reasons are those axioms. They're what's driving the rationality. And we know the motivic zeta function is not rational because I told you Larson and Luntz said so. But you can even prove it now. I'm going to give you the proof. Well, I'm not quite the proof. I'm going to tell you the motivic measure they used. So here's the Larson and Luntz measure. So I've got to define it for smooth projective varieties, and then show that it plays well, that it respects Bittner's relation. And so here's basically what it is. It's a polynomial where you take 1 plus the number of 1 forms plus the number of 2 forms, all the way to the number of n forms. This is sort of part of the Hodge diamond. And it lies inside this ring. And there we go. And then I should just say I can note that you can, if you think about this, you can show that L goes to 0, because that's not, I do indeed, thank you. There's a t squared, great. I think that's, if I've forgotten the others, let me know. And that's true because you can just work out what mu of P1 is, that's smooth and projective, and you can work out what mu of a point is, and that's smooth and projective. Well, in fact, I'll tell you what they are. Mu of P1 is 1, mu of a point is 1. So we've proved that mu of L is 0. And so if you want to show that it respects Bittner's relation, you can go and think about that, and you'll be able to do it. It's not very hard to do. And so bingo, they have a measure, but then they have to be clever to show why is the thing not rational. Well, why when you take this measure is it not rational? That I won't do. Okay, so great. So the conjecture that the motivic zeta function was rational was false. But I want to say that even though it was false, it took us to some really interesting places, including this approach, this way of thinking about things like about Hodge theory and the Vey conjectures, and also interesting things like this as well. So I want to state some more, tell you about some more conjectures. But as I mentioned informally last time, conjecture means speculation, means question in this area. No one has, I feel like no one a proof or a disproof would be happy for any of them. I now am of the opinion that all these conjectures are wrong, but they're all wrong for interesting reasons. So I'll now tell you a bunch of these. And so let me give some motivation for a conjecture that Melanie Wood and I made. And I think the main thing I want to sell is the conjecture, since I feel like you want that this question is interesting. And so here's the motivation for it. So the Vey zeta function for x for a variety over fq, well, it's, again, I'm going to separate, not do Euler characteristic, but do if it's dimension d, then it's this rational function, and the little pieces have to do with the cohomology, which we've already even seen, well, we can even prove using our proof of the rationality of the Vey zeta function. And so I want to ask about the coefficients, about how do the number of points grow. And if I give you a power series, I'm going to go back to a question from sequences in series from back when you were 7 years old. And so you have a, so if you have if I give you a power series, and I want to know how the coefficients grow, but I tell you it's a rational function. I even describe it as a rational function. And I say, how does it grow? Well, what you'd quickly realize is that you do partial fractions, and you realize that the smallest root, like the smallest root of the denominator, or the biggest inverse root, is the thing that's going to drive it. That when you invert it, then you'll get, that's the thing that's going to push things, that it'll grow like the powers of the inverse smallest root. So, well, let me, rather than go into details, say that what this means here, part of the Vey conjecture is say that the size of the roots, this guy is going to be the biggest root in size, and I should say this guy is 1 minus q to the d times t to the 2d. Times t. Great. And so what this means is that these things grow like q to the d to the I, or to the n. Let's make that n. And so what have we done? What does this mean? These are actually the Hasse-Vey bounds. So this is, these are, I should say, essentially are akin to the Hasse-Vey bounds. And the one thing I want to mention is that even before we knew the rationality of the zeta function, we knew the Hasse-Vey bounds. So somehow this is an easier fact than rationality. And so the proof does not actually use that rationality, or the original proof, or the proof does not use that rationality. Okay, so now let me actually try to make the same thing work for the motivic zeta function, and I'll get something which you'll think is very strongly motivated from number theory, but then I'll tell you why it's actually very strongly motivated from topology for completely different reasons. So here's the conjecture, which I'm going to call the motivic stabilization of symmetric powers. And this is with Melanie again, I should say, and let me just abbreviate it because that's a mouthful, as MSSP. And so here's what I want to say. I want to say that what's the coefficient of the motivic zeta function, that this should grow like L to the n as n gets big. But what does that mean? Let's put the L to the n over here. And that should converge to some finite thing. Well, what does that mean? Well, what is this thing? It's got an L in the denominator, so we can't divide by L unless we invert L. So this is actually something inside our ring localized at L. But the limit might have more and more L's in the denominator, so we're going to want to complete by allowing L's all the way out. And so the statement should be that this converges in this topological ring. In other words, there's a question? We should indeed, thank you. That should be dimension x. And there should be there, but it's crossed out. That's right. And so if you plug a q in here, if you plug L equals q, you're going to get the Hasse-Vey bounds. So this converges, and well, that's the conjecture. And let me try to motivate what it means, or why you should believe it or hope it's true. In the same way that you have to believe that the motivic zeta function is rational. So this may not be true, but still, I'm going to try to convince you should want it to be true, and then be interested in how it can be false. Okay, so here's, so let's see. So we have evidence of some sort, which is, so for example, we can, when we specialize the point counting, well, we already know the Hasse of A, we already know that over FQ, so that works then. Hodge, we know it's true for Hodge structures because, well, basically because of Chia's argument, of the argument we just gave, that zeta function is rational, so the same argument is going to work. That means it's also true for curves because the zeta function, motivic zeta function of curves is rational, so that's maybe a little bit lame because all these examples are just from rationality, but it's also true for any stably rational variety whose zeta function may not be rational. So maybe that's convincing, or in some sense I don't think that should be too convincing, but I could try to fool you to make you think it's convincing. And great. So all of these feel like they're number theoretic. But there are actually topological reasons for this too. And maybe good, more paper. That was a close one. Otherwise, everything else was going to be on one slide, and that would be really bad. Okay, great. So there's a topological reason too. So now I have to tell you a little bit about topology, and this is I guess the blind leading the blind. Given that I'm not a topologist and you're not a topologist, but that means that you can't catch any mistakes I make. Here's the top. So here's what life looks like at a topology conference. If you have a reasonable topological space with a point P inside it, then you have symmetric powers of X, and you have this map to where you just sort of add the extra point on. So you have this whole sequence of symmetric powers. And so long before arithmetic and algebraic geometers got to this, the topologists showed that as you fold this along, as n gets bigger and bigger and bigger, that this stabilizes in some sense. So maybe the first approximation, although this is weaker, although it gets better, it means, for example, if you're interested in the 51st cohomology group, if you go far enough out, eventually it becomes an isomorphism on the 51st cohomology. But it's even better. The homotopy type, sort of up to codimension 51, will stabilize when you go far enough. So in other words, it becomes kind of like a homotopy equivalence, but up to a certain, let me say codimension, even though that's not the right thing to say. Okay, so and I should say better yet, they even know when. You want to know when HI stabilizes or when the homotopy up to codimension 3 stabilizes? There's even an effective bound that's saying when it does, and you can so you can just ask Arnav Tripathi, who will explain it to you, because there's sort of a slick way of seeing it where it becomes you can really understand it. Okay, so that means you have some limiting homotopy type, which is sim infinity, and we even know what it is. We know that it's the product of things that are k where you put the k pi n's, where I always forget how to write this. There's the n and there's the reduced homology of it. So somehow you've taken this thing which is complicated and broken it up into pieces where you can read off the individual cohomology groups. And if you might remember that part of the axioms, one of the standard conjectures is if I give you something complicated and geometric, can you pick off the different HIs? So can you make sense of that? Okay, great. So that's one example of a stabilization result in topology. And such results long predate our understandings in algebraic geometry. Horror stability is another example. And I want to maybe say that there's this theme in a very active, exciting area of thought in between many fields called stabilization of stuff, although that's not the official name, which kind of says that you should, when you have a sequence of things, often many arithmetic, algebraic, etc. things are somehow stabilized. Each individual case is confusing, but the limit's really nice. And the topologists also were here long before, because each of these sim n's is pretty interesting and good, but it's a sim infinity, which is really beautiful, which really lets you unpack what's going on in X. And you should just instead think of all these as approximations to sim infinity as you add more and more and more points. Okay, so I want to mention two results in this vein, which is, so the first, yeah, great. I think I will definitely, maybe I will just mention one of the results. No, I think I'll briefly, think I should be able to mention two. Well, I mentioned in the opposite order, which is first this is the theorem of Arnaud Tripathies from this year, that the symmetric functor in a tall realization, so the space you get basically by looking at the Étale topology and trying to make a space, that these are both functors, that they commute. And if you've thought about Étale things, especially Étale homotopic things before, you'll realize this really, this immediately gives you a lot of excellent consequences, including kind of an Étale-Dolton theorem, kind of an Étale kind of Dolton theorem. And now, chronologically, I'll go backwards now and mention something, which is, so algebraically, X in X cross A1 should be homotopic, whatever that means. And you could, I don't know, invoke Voevodsky or just invoke your belief in the goodness of nature, that these should be homotopic. But sim n of X in sim n of X cross AM even look very different. It can be, these are very different spaces. So for example, we'll think it highly singular. And there's a theorem, it was just an observation, this result, which I'll call, it's a trick of Bertottaro's, but it's a one-line, well, it has a one-line proof, but people should have come up with it a long time before. So let me tell you the result. He wouldn't have said it this way to begin with, but in this Grothendieck ring, if you take sim n of X cross AM, you get the same thing once you cut and paste as cross A MN. I hope I have that right. My M's and N's right. So whatever that is to make that dimension work out. So what he really showed was that you can cut and paste this guy and rearrange the pieces to get this guy. And then I should say, what I should say he really showed was a case where X was a point, but then his argument works just fine for a general X. And so this is, so maybe let me say explicitly, here's the statement that you might be able, here's a statement that people should have known, that sim n of AM is AMN, at least in the Grothendieck ring. So a very basic statement, I should say, and there's a long body of work. On this sort of thing where at some point someone proved that this was rational. But that's kind of obvious now when you kind of see, so all sorts of things here become really easy. And so now I'll say a couple things. He has a one-line proof. So the question is, find the one-line proof using Hilbert 90. And the people who were thinking about this did not think in the Étale topology. So that's why I think they missed it. And then after the fact, this is in the 2000s, people actually figured out how to cut and paste it. So if you know it's cut and pastable, you should be able to figure out how to do that. So maybe that's the other, maybe more challenging question is somehow there's some nice structure here that's indicated by the Grothendieck ring as well. And I should say also this is true for counting points. I mean, and this plays well with counting FQ points, which is also not necessarily so obvious either. Great. So this is something which really should have been known in the 19th century. So tomorrow when I resume, what I'm going to do is tell you about some other conjectures and later on how they're actually all wrong, but how they're all wrong in an interesting way, and from that take us back into arithmetic.